We're going to consider now a collection of theorems, and these theorems are going to tell us whether or not a given series converges. Notice that we're not interested in what the series converges to at this point. These theorems only address whether or not the series converges or diverges. And the first test that we should always use whenever we look at a series is what's called the nth term test for divergence. And there's two ways of stating this test. The first is that if we have a series whose terms are an and they're non-negative numbers all in the series, then if the sequence of the series terms does not converge to 0, then the series itself cannot converge. And an equivalent way of saying that is that if the series sequence terms an are non-negative real numbers and the series of those terms converges, then the terms in the series have to converge to 0. Now, it's important to understand what this theorem is saying and what it's not saying. Okay. Notice that if we look at the second form of the theorem, it's an if-then statement. It says if the series converges, then the terms in the series have to converge to 0. And it's important to understand that in a conditional statement, if we have a statement like, say, if P then Q, which is true, it doesn't follow that the converse is true. In other words, it's not necessarily the case that when we switch those conditions, the statement is still true. And a good example we've already seen from last section. If we let P be the statement that a function is differentiable and Q be the statement that a function is continuous, the conditional statement if P then Q is certainly true. If a function is differentiable, it certainly is continuous. But notice that when we switch those conditions, that statement's no longer necessarily true. It's not necessarily true that if a function is continuous, then a function is differentiable. So we can't just switch these two statements. So notice that even though the statement, if the terms in this series don't converge to 0, then the series does not converge, is true. It's not true, necessarily, that if the terms in the series converge to 0, then the series itself converges, okay? So in other words, this is kind of equivalent to swapping the conditions from this form of the theorem. Okay, this is not necessarily true. So it's important to realize that this theorem only tells you when a series does not converge. This is kind of the key point. Okay, it does not tell you when a series will converge. It only tells you when it won't converge. So in other words, this condition that the series terms have to go to 0 is necessary. We have to have it, but it's not enough to guarantee the series itself will converge. And let me show you a famous example that illustrates this. This is called the harmonic series. Okay, this is the sum of 1 over n. So this looks like 1 plus 1/2 plus 1/3 plus 1/4 dot dot dot. Notice that the terms in this series go to 0, but this series is known to diverge, and in fact we're going to show this in this video. So this is a classic case of where the terms in the series go to 0, but the series diverge. So this is not a strong enough condition to guarantee series convergence, and this is why I say this theorem cannot tell you when a series converges, only when it diverges. Okay, next we want to move on to, and by the way, this is always the first thing we check. If we can, sometimes it's difficult to tell what the limit of the terms in the series are, but if we can, we always want to check that and convince ourselves that this is true. Otherwise, it makes no sense going on and thinking about what the series converges to if it doesn't even converge. Now the next thing we want to do is we want to look at tests for conditional convergence. And we're going to limit ourselves to a specific type of conditionally convergent series. It's called an alternating series. So this is a series where the signs, the algebraic signs of the terms in the series alternate, plus, minus, plus, minus. And we want to know under what conditions this alternating series will converge conditionally. And it turns out that if the terms in that series meet two conditions, first, that the magnitudes of the terms are decreasing, and second, that the terms themselves converge to zero, then we're guaranteed that that alternating series will converge conditionally. And I have to put this term conditionally in, okay? And a very famous case of this is what's known as the alternating harmonic series. Notice this looks like the harmonic series. It has a sum of 1 over n, right? There's 1, 1/2, 1/3, 1/4. But what makes it alternating is the fact that the signs alternate. So this is definitely an alternating series because the signs are alternating. And notice that it satisfies both conditions for us to use this theorem. First, if we look at the magnitude of the terms, okay, they are strictly decreasing. And moreover, if we look at the terms themselves in the series, they're converging to zero. And so these three facts together tell us that the alternating harmonic series converges. It doesn't tell us what it converges to, but it tells us that it converges. And we're going to show later on that it actually converges to the natural log of 2. That's not difficult to show. Now, we said before that we weren't really particularly interested in conditionally convergent series, and that's true. However, when we start to do Taylor series and we're trying to look at the endpoints of the radius of convergence for a Taylor series, we're going to find that these alternating series occur very commonly. So we're going to have to deal with them in special cases, and this is how we do it. This is the theorem that we're going to use. And that's all we're going to say about conditionally convergent series at this point. We want to move on and we want to look at absolute convergence. And we're now going to consider 5 different tests for absolute convergence, and we're going to look at the very first of these tests in this video. It's called the integral test. And what it says is that if we're given a series whose terms are non-negative real numbers, and the explicit function for that series can be represented by some function f that is continuous and decreasing, then the series converges if and only if the integral of that function from 1 to infinity converges. Okay, so those quantities either both converge or both diverge. And there's a very famous example that we want to look at. And by the way, I'll just mention very briefly why this theorem is true. I don't want to get into a long aside, but basically if we think about what this integral from 1 to infinity of the function is, basically it's the area under this curve. Notice that the function is actually equal to the values of the sequence at the integer values, okay? So the area under this curve is this integral. And if we think about what the sum of this series is, it's actually the area under these rectangles. Okay? It's the length, which is 1, times the height, which is the value of the term in the series. And so intuitively it makes sense that if one of these is infinite, the other one will be infinite. If one of these is finite, the other one will be finite. Okay? We can make that notion very rigorous mathematically, but this is just kind of the kernel of the idea underlying this theorem, okay? But we want to look at this theorem because it's especially important in looking at the convergence of what we call the p series. So when we have the series of 1 over n to the p power, where p is greater than 0, we call this sort of series a p series. And a very important question we want to try to answer is, for what values of p does this series actually converge? And the way we address this question is, we notice that we can give the explicit function for the terms in the series by f of n is equal to 1 over n to the p. Okay, in other words, you tell me what n is, and f of n gives me the values of a sub n. Okay? And so I'm going to use that to consider the function f of x now, where f of x is 1 over x to the p. And you'll note that this function satisfies the condition of the theorem. It's both continuous and it's decreasing because we're raising this x to a positive power. So as x gets larger, this also gets larger. Okay, and therefore the ratio, the reciprocal gets smaller. And before we get into actually applying the integral test, I want to remind you of a fact from calculus. We haven't technically done this, but I'm sure you remember this. It says that the integral of x to the n is equal to the natural log of x if n is equal to -1, and it's equal to x to the n plus 1 divided by n plus 1 if n is not equal to -1. And so I want to use this to now evaluate this integral. And whenever we have an integral where one of the limits is infinite, we have to consider that an improper integral. So what we do in this case, since the upper limit's infinity, we make the upper limit some dummy variable t, and then we let that go to infinity. That's how we correctly do an improper integral. And we notice that when p is equal to 1, this becomes x to the -1, and of course that integral is natural log of t. And when we evaluate this out, we see this is going to be infinite. So this tells us that since the integral is infinite for p equal to 1, the p series also will be infinite for p equal to 1, and it will not converge. Now if we consider the case when p is not equal to 1, we're going to get the following result applying this rule for the integrals. And you can see that the key thing is to look at the two different cases. When p is between 0 and 1, you notice that this thing is positive. Okay, the exponent on t is positive. So as t goes to infinity, this quantity is going to go to infinity, and the integral will be infinite. Similarly, when p is greater than 1, we notice that the exponent on p is negative. So this becomes t to a negative power, and as t goes to infinity, that quantity goes to 0, and the integral goes to 1 over p minus 1. Okay? And so now we can reach our final conclusion, which is when this p series converges. We see that when p is between 0 to 1 inclusive, the p series diverges. And when p is greater than 1, okay, the p series is going to converge. Now it's important to understand that this value of the integral is not equal to the value of the p series, okay? The integral, we're only interested in whether it's infinite or not. That's going to tell us whether the series converges or not. The actual values of the p series generally require some additional mathematics, advanced mathematics. And when we do Fourier analysis, we're going to actually develop rules for analyzing these p series. We're going to see, for example, that when p is equal to 2, the p series converges to pi squared over 6, and we're going to actually probably devise a bunch of little nice facts like that. Okay, that's all for the first set of theorems on series convergence.